So in this video, we are going to explain how to plot the bifurcation diagram for continuous time systems using the technique of local maxima. Okay, I already have another video on my channel on how to plot the bifurcation diagram, but in that video, we are using a different technique. Okay, which takes advantage of the so-called Poincaré section or Poincaré cut. Okay, the technique I'm going to show you today, it's much easier to implement and actually much faster and much more consistent. Okay, so you can watch that video as well and then watch this one, of course. Now, the results that I'm presenting come from a very recent paper on continuous time density-colored bifurcation diagrams. Now, I will upload another video specifically about density-colored diagrams, which is a very specific and much more interesting tool, which is a variation of the bifurcation diagram. Okay, but on this video, we're only going to discuss the real classic bifurcation diagram using the local maximum. Now, I don't know how familiar you are with the basics, so let's start with some very specific information about continuous time systems. Okay, so we see these systems continuous time because they evolve over a continuous interval. Okay, so time is continuous in this case. Okay, in contrast to discrete time systems. So time usually starts from zero and goes to infinity. Of course, the starting position may not necessarily be t equals zero. It may be some other initial condition, but usually it's from zero. Of course, in the general case in physics and mathematics, we may consider trajectories going from minus infinity to infinity. But for our specific application, the classic case, we go from zero to infinity. Okay. So since we have continuous time, the evolution of this system is described by a set of differential equations. Okay, so we have x dot, the derivative of the system, equals to some function of f. And the x, of course, is a state, so it's not just one state, it's a state vector. Okay, so we may have x1, x2, x3, x4, and whatever, okay, how many states of the system. Okay. Continuous time systems usually model circuits, mechanical systems, fluids, masses, or any other other type of what we would say a flow. Okay. In discrete time systems, for example, we mostly use them to model economic systems or biological systems. Of course, this is not exclusive. We may model continuous time economic systems as well. Okay. So, for continuous time systems, of course, we all had some courses on differential equations, so we know that there are ways to actually solve them. But here, since we're dealing with highly nonlinear systems and chaotic systems, the way that we solve them, and specifically in our numerical simulations, we do them using numerical techniques. Okay, so of course, many programming languages already have many routines to solve systems. I'm going to use MATLAB. MATLAB has many built-in functions to solve systems numerically. Okay, so you don't need to know many details about the techniques. Just know the very basics that we're talking about continuous time systems. But when we're solving them numerically, basically, we have to discretize the time. So we choose a very small discretization interval, okay, 0.001 second, for example, and we obtain the solution at discrete time intervals. Okay, so we start with t0, which may be 0 for example, t0 plus h, t0 plus 2h, and so on, until we reach a desired simulation time. Okay, so this is the very basic you need to know about numerically solving continuous time systems. Okay, and finally, side note, chaos in continuous time needs at least three dimensions, and by that I mean at least three states, okay, in order to have chaos. So a two-dimensional system cannot be chaotic if it's autonomous. Okay, this is because trajectories cannot intersect, trajectory cannot intersect itself. I'm not gonna go into details about that, okay? So these are simply the basics about continuous time systems. So let me explain what is chaotic behavior. And I'm going to explain this through a very classic example. Okay, the Rossler system. In my other video, I talk about the Lorentz system, but here I have chosen the Rossler because it has a very nice diagram, as we will see. Okay, very classic system. It is described by three differential equations, the one that you see right here. So we have three states, x1, x2, and x3. Okay, and the system has three parameters, a, b, and c. And I can solve the system by choosing an initial condition, a starting point, okay, and different parameter values. And as we will see, for different parameter values, the system has a very, very rich behavior. But let's start with the most basic behavior that we want to talk about, the chaotic behavior. Okay, so what does it mean that the system is chaotic? Let me explain. So here I choose a set of initial conditions. So what you see here at time 0, I choose x1, x2, and x3 all to be equal to 0.1. Okay, this is my choice. And then I set some parameter values. Alpha, which is the parameter that we will study today, is 0.45, b equals 2, and c equals 4. And what you see right here is the solution of the system. Okay, I have solved it numerically in MATLAB. This is the solution for 600 seconds, and it is plotted with respect to time. So the x-axis is time, and the y-axis in each graph is the first, the second, and the third state. So what do we see here? You see that the solution of the system is very, very, very complex, right? What do I mean by complex? Basically, what do I mean is that this solution does not repeat itself. Okay, I can state this by saying that the solution is aperiodic, okay, non-periodic. If you study any specific state individually, you will see that the state goes up and down continuously, but the pattern doesn't repeat itself. Okay, actually, there is no pattern. Okay, so the solution here is aperiodic, meaning that it never repeats itself. Okay, and of course, here I have plotted 600 seconds, but if I plot even more, 1000 seconds, 2000, 10,000 seconds, you will observe the same thing. Eventually, the trajectory will never repeat itself. It will remain aperiodic through and through for all time. Okay, so this means that the solution is chaotic. It is bounded, so it doesn't go to infinity, but it also doesn't converge to any given state or pattern. Okay, so it is bounded and aperiodic, which means that it is chaotic. Okay, but there is also one more detail I will explain in a moment. Now, this solution is plotted with respect to time. Okay, another thing that we can do, and you have probably seen it even in some pop art, maybe, or pop culture, is we can plot the three states not with respect to time, but with respect to one another. Okay, so instead of plotting x1 with time, x2 with time, x3 with time, I plot them together. So x1 with respect to x2 with respect to x3 in this graph right here. And here I have the two-dimensional graph. So x1 with respect to x2, x2 with x3, x1 with x3. Okay. This is called the phase diagram or the phase portrait of the system. Okay. It gives us a very nice information. It tells us basically, sorry, how do the states evolve with respect to one another over time. Okay, and this graph is very interesting because you will see that we obtain a very weird shape in the phase space. Okay, this shape, which is basically the shape of how the three trajectories interact with one another, is called an attractor. Okay, specifically, we also call it a strange attractor of the system. Okay, so if you ever hear the term strange attractor, it means this. It means the solution of the system plotted with respect to with respect to the individual states, okay, instead of with respect to time. So this is the attractor for the Rossler system, okay, and it is chaotic, and we see this non-repeating pattern appearing, okay. Now that the system is chaotic, it has also a very, very, very nice property. What is this property? To understand this property, we need to simply plot two different solutions together. So what have I done here? I have plotted two solutions, okay, for two different initial conditions that are only very, 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 very slightly different from one another. So these are the solutions right here. You will see that the first state is the same, the second state is the same, and the third state is almost the same. The one is 0.1 and the other is 0.10001. So basically, we have two different solutions that start from almost identical initial conditions. They only differ to the extent of 10 to the minus fourth. Okay, so we have a very minuscule change. So see what happens if I can actually zoom in right here. You see that for all three states, okay, for the first around 100 seconds, the solutions are exactly the same. You see that one is plotted in black, the other in blue. You cannot see one another, you cannot distinguish them because they are very close to each other. Okay, so initially, oops, I'm sorry, let's go back here. So initially, the solutions are almost identical. But what happens? Slowly by slowly by slowly by slowly, over time, this minuscule change or this minuscule difference in the initial conditions starts to become larger and larger and larger and larger and larger until eventually, here we see around 100 seconds, what happens? The two trajectories begin to diverge from each other. And after 105 seconds, they become completely different. Okay, so if you see after 100 seconds, all three states become completely different from one another. Okay, so what happened? We started with a minuscule change in the initial conditions. Okay, and after what? 100 seconds, it can be lower or higher sometimes depending on the system. Eventually, the two trajectories which initially seemed to be the same, eventually became completely different. Okay, so a minuscule change at time zero over time brings about completely different solutions. How is this phenomenon called? You may have heard it, of course, in pop culture. This phenomenon is called the butterfly effect. Okay, this is it. If you have heard it in pop culture, this is the butterfly effect. Very small change in the initial conditions over time leads to completely different solutions for the two systems. Okay, so this is a very characteristic behavior in chaotic systems. They showcase the butterfly effect. Okay, what is more interesting though is this. If I actually plot the phase portraits for the two solutions, see that they are not the same, of course, but both of them, okay, although they are not the same, both of them create a very similar shape in the state space. Okay, so although the solutions are not the same, the attractor they form has a very similar shape. Okay, so basically this tells us that although we have different solutions, okay, qualitatively, these solutions showcase similar characteristics. So this is another very important phenomenon in chaos. Okay, now that's with the basics of explaining chaotic behavior. But the Rossler system, pretty much like any other chaotic system, doesn't just showcase chaotic behavior. Okay, so chaotic systems usually have a very rich series of dynamical behaviors that is not limited to chaos. And the thing is, how can we identify these behaviors? So let's talk about the technique in identifying them. So let me show you, for example, another solution of the system for a different set of parameters. So I have kept B and C the same, and A here, instead of 0.45, have set it to 0.3. And for 0.3, we obtain this solution right here, okay, for 600 seconds. First of all, let me note something very important that we are going to use, okay, in the future. You see that I have marked with blue the first few seconds of simulation, okay? You see that the system starts from the initial condition, it does some oscillation, and eventually, after 30 or 40 seconds, settles up into a repeating pattern. Okay, so previously we had chaos. Here we very clearly do not have chaos. All right, because if you see all of the states, all of them showcase a pattern. Each state x1, x2, and x3 goes up and down and it basically repeats itself. Okay, so here, for example, the behavior is very clearly not chaotic. But as you see, this didn't start at time zero. We started from the zero place, 0.1, and slowly by slowly, how can I say this? We converged to the periodic behavior, okay? So this transition that we did from the starting position until we reach the final behavior of the system, okay, this is called the transient behavior. And when we are trying to qualify or maybe quantify the behavior of the system, this transient is not of interest to us. The transient behavior basically tells us how does the system transition from its starting point into its final behavior. Okay, so just a side note, very important side note. when we're studying chaotic systems, and for that matter, any other type of system, the transient, which is just couple of seconds, the initial seconds, which can be 50, 100, 200 seconds, we usually discard this. We don't take this into account. Okay. So here the system is clearly periodic. Okay. But how can I say this? Is there a way to formally evaluate it? Yes, there is. First of all, let's plot the phase portrait. And as you see, because the system is periodic, the phase portrait looks something like that, after I have discarded the transient, of course. Okay. You will see that it's basically a curve, a closed curve that goes around on and on and on. Okay. And in order to quantify what type of behavior I have here, the best technique, and it is basically the technique that we will use in the bifurcation diagram, is to consider any state of our choice, x1, x2, or x3, doesn't matter, and plot its local maxima after we discard the transient. Okay. So here, for example, I have the first state of the system, I discard the transient, and I plot the local maxima. And you will see that the local maxima are the blue dots right here. So what do we observe? Basically, all the local maxima are the same value, which is very close to 4. Okay. So from that graph, we can evaluate that for this case, the system is periodic and it has a period 1. That's how we can quantify period 1, because we basically have a single local maxima for this state, but it also holds for the other states as well. Okay. So this is period 1 behavior. Now, let me give you another example. Now I have changed the parameter of alpha. We have alpha equals 0.35. And again, after I discard the transient, you see this behavior in the system, which is, again, very clearly not chaotic. It is actually periodic. But you see that it's different from before. Okay. Again, we have a repeating pattern in all states, but it is not the same as in the previous graph. If I plot, of course, the phase portrait, you see this graph right here. It is again a closed curve, but it has sort of a double route that it follows. It goes, if you follow my mouse, up and down, and then again up and down, and it repeats itself. Okay, so the behavior is slightly different from before. And how can we quantify this? Well, we can quantify this by plotting again the local maxima for any state of our choice. We can go again with state 1. So you will see right here that now, different from the previous case, I have two distinct local maxima. Okay, the trajectory goes up and down, but the local maxima, as you see, are basically these ones right here, which are repeating itself. So it's first, second, first, second, first, second, first, second, first, second. Okay, so we have two distinct local maxima. And this tells us that we have a periodic behavior, and we can name this behavior period 2 behavior, because we only have two distinct local maxima, right? So let me give you another example. If I change the parameter again to 0.38, you see this solution right here, and this solution is again non-chaotic, very clearly, we have a pattern, but it is different from before. If I plot this phase diagram, you see that now we have this sort of closed curve again, but we go higher up 2 times and higher down 2 times again. So we go up and down and up and down 4 times overall. But how can I very clearly quantify this? Again, by going and plotting the local maximum. So for the first state, now you can very clearly see the blue dots. We have 4 distinct local maxima in the system. Okay. So the behavior is periodic, and we can call this behavior period 4, okay, because we have 4 distinct local maxima. Up, down, up, down, up, down, up, down. Okay, 4 different local maxima, so a period 4 behavior. Okay, so we can have many types of periodic behavior. I showed you 1, 2, 4, you can have 8, you can have 16, but also you can have chaos. Okay, so for A equals 0.45, this is the chaotic attractor that we have already seen in the previous graph. Okay, so the system here is chaotic, and how can I quantify that? using the same technique, local maxima. Okay, and as you see right here, I have 800 seconds of simulation. You see that the local maxima, after we discard the transient again, are non-repeating and are basically all over the place. Okay, you see that since there is no repeating pattern in the system, and since the solution is aperiodic, naturally the local maxima are also aperiodic. Okay, that's why we see a graph that looks like that. Okay, and of course, even if I consider even a longer simulation time, for example, here I have 4,000 seconds of simulation, and I have all the different local maxima plotted. Again, you see that the local maxima don't have a specific pattern. They pretty much fill all the space in the state space. Okay, so we have non-repeating pattern. So naturally, the local maxima are basically innumerable. We cannot count how many of them they are, and they are dispersed all over the place. Okay, so as you can understand, this system has many different types of behavior. I showed you period 1, period 2, period 4, chaos, but these are not the only ones. It actually has more behavior. Okay. So how can we analyze the system? Okay. How can we have a tool that tells us that, look, Lazarus, for this specific parameter range, the system behaves like this, like this, like this. How can we do that? Well, this brings us to the bifurcation diagram. Okay. So the bifurcation diagram is exactly this. It is a tool that it is built for giving us information about how a system behaves. So what is it? Well, it is a diagram. It is a two-dimensional diagram that gives us qualitatively what is the behavior as a specific parameter changes. Okay. So what do we do that? How do we do that? Basically, on the x-axis, we put the different parameter values that are of interest to us in a specific range, let's say from 1 to 10 or from 1 to 100, doesn't matter. So on the x-axis, we have the parameter values of choice, and on the y-axis, we have some information about the qualitative behavior of the system. So what is the qualitative behavior that I have showed you so far? What is the tool that we can use to quantify the behavior of the system? The local maxima. Okay, so the diagram has exactly that. It is a two-dimensional graph. On the x-axis, I'm going to put the different parameter values that I want to study for the system. And on the y-axis, each time I'm going to plot the local maxima for this specific solution, for this specific parameter value. Okay, so basically, to plot the bifurcation diagram, all I need is a very simple loop in any programming language. Okay, so let me give you the pseudocode. This is the pseudocode to plot the bifurcation diagram, and I will probably make another video about the bifurcation diagram. And also I'm going to put about the code of the bifurcation diagram, and I'm going to put a link into the description for you to download the bifurcation diagram code in MATLAB. Okay, so we start by choosing the bifurcation parameter. In my example, I'm going to study the parameter A for the system. Okay, so I'm going to study the behavior for parameter A. Now, I'm going to set the values for my other parameters, B and C. Okay, and I'm also going to set the initial conditions of the system, x1, 0, x2, 0, x3, 0. Okay, now for the parameter under study, I want to choose a bifurcation interval of interest. Here, for example, for the Rossler system, I'm going to study how it behaves when alpha goes from 0.3 to 0.45. Okay, and for this interval, I'm also going to choose an iteration step. Basically, how do we have increment, how we increment from 0.3 to 0.45? A very small value in order to have the diagram. So how does the diagram works? We start with a for loop starting from a equals 0.3. So what do we do now? We have our parameter. We simulate the system for a considerable time. Okay, depending on the system, we may need to change that. But I would generally suggest 4,000 plus 500 seconds, even more. So we simulate the system for a considerable time. Okay. Then we discard the transient behavior. Okay, remember, we are not interested in the transient. I would suggest discarding 500 seconds. Okay, of course, this depends on the system as well. So after we discard this transient, what do we do? For the rest of the solution, we find the local maxima, okay, for any chosen state, x1 or x2 or x3 or whatever state you like. Choose a state and stick with it. The result is going to be the same qualitatively, okay. So after we find the local maxima for this solution, what do? We plot the local maxima vertically as these points. So the x-axis, the x value is going to be the parameter alpha, and the y value is going to be the different local maxima that we found for any given state, let's say for the state x1. Okay, so this is just what you do. Okay, after you do all that, you change the parameter of alpha, you increase it a little bit by the increment step epsilon, and repeat it again. Solve the system again, discard the transient, find the local maxima, plot them. Then you increase the value of alpha again. Simulate the system, discard the transient, plot the local maxima, and then repeat again. Increase the value of alpha, simulate the system, discard the transient, plot the local maxima, and so on until you complete the whole bifurcation interval. Okay. As a single side note, take a look at the red line. The diagram that I have described is the classic bifurcation diagram. But a variation of this, what people do is this. Each time they complete the solution of the system, what they do is they set the initial conditions equal to the final conditions of the current simulation. Okay, so after you simulate the system, you plot the local maxima, you change the initial condition. You set x0 equal to the final value from your simulation, okay? This variation is optional. This is called the continuation diagram because it's basically you solve the system, and from the time that you have stopped, you simulate the system again, and from the final state, you simulate the system again and again and again. Okay, this is called the continuation diagram. While in the bifurcation diagram, the initial condition x1, 0, x2, 0, and x3, 0 is the same. And that's what I did here. So basically, it doesn't change the time the code takes to execute. It's just a simple variation. But I'm giving you the bifurcation diagram from fixed initial conditions. Okay. So we basically plot the local maxima for each value of the parameter, okay, and each solution. The graph that we are going to get looks something like that, okay. So on the x-axis is the different values for the parameter alpha, okay, and on the y-axis what you see is basically the different local maxima for the solution we have obtained each time, okay. So basically, this diagram immediately tells us qualitatively how the solution behaves for each parameter value. We can understand immediately that on the points, for example, from 0.3 to 0.30 something, we have a single line, a single point. What does that mean? This means that for 0.3, 0.31, etc., we only have a single local maxima for the first state. Okay. So for 0.3, for example, single point means period one local maximum. For this range right here, from 0.33, I guess, to 0.36 or something, we have 2 points vertically, okay? Look at this time, look vertically the diagram, okay? So in this case, for example, for 0.35, since we have this point and this point, 2 points means 2 local maxima, so a period 2 behavior. And you see that as the parameter increases, we went from 1 local maxima to 2 local maxima, and then we go after 0.36, 37 to 4 local maxima. So here we have period 4, and then you see that all of the other regions are dense. Okay, why are they dense? These regions that you see here that are very, very black, this means that we have many local maxima that we cannot really measure them. Okay, so all of these dense black regions right here indicate, just like the case of 0.45, that we have chaotic behavior. Okay, so immediately using this graph, we can understand what are the periodic behaviors in the system, okay, which are the chaotic behaviors in the system, and moreover, how we transition into chaos. So for example, we see that the transitioning here goes from period 1 to period 2 to period 4 to period 8. Basically, this very, very small region right here that you see goes from period 8, 16, 32, and so on, and then into chaos. And in between chaos, I don't plot them right here, but these white regions that you see is basically cases where we go from chaos to periodicity again, from chaos to periodicity. So you see that once we achieve chaos, we don't necessarily keep chaos in the behavior. We may go from period to chaos, but we may also go from chaos to period, okay, to periodicity. So for this system, for example, we see that chaos is interrupted by very, very small gaps, as you see right here, of periodicity. Okay, so this is the bifurcation diagram, and this is what it shows us. And of course, you can go into much, much further detail in all of these small subregions in the diagram. Okay, so for example, I see that in this very, very small region right here, we have chaos, and then chaos becomes interrupted by periodicity, and then chaos again, a little after 0.4, right? So I can go, for example, and if I want to, I can choose this very small region, okay, and do a separate bifurcation diagram at a much smaller step, of course, iteration step, for just this specific region. And it is very amazing because you see that if you zoom in just in this very small, very, very small region, you will see again a repeating pattern of going into chaos by starting from period 3 this time, because we have 1, 2, 3 local maxima, and then you go to 2, 4, 6 local maxima, and then we go towards more and more local maxima until we reach chaos. So you see a very, very analytical analysis for this specific subregion, and of course you can do the same thing with any other subregion in the graph, right? So this is the bifurcation diagram. Okay, I don't have anything else to say. I want you to understand what the diagram represents qualitatively. Okay, and after that, you can also read the full-length paper that I told you about. Watch the MATLAB code that I have in the description of the video, download it, make any changes that you like and implement it in your own systems. Okay. And then I'm gonna make another video where I discuss a variation of this diagram called the continuous time density-colored bifurcation diagram, where we basically have a variation of this diagram that uses color to indicate density of local maximum. But I'm going to show this in a video or in a next video, in a different video. Okay, so any questions that you have, write them down in the comments, download the code, play for yourself, try variations, okay, but also read the theory to understand qualitatively what the diagram represents. So thank you very much.